Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends, students, and whoever is taking this course, project management. And by this time, I am sure you know my name by heart, and obviously you know the contents of this project management, the concepts much better than me, considering that we have been discussing many of the issues, and you would have done many of the assignments like as per the norm after first week, second week, third week, fourth week, fifth week, and all those things. And to also remind my dear friends, this is the 39th class, and there will be another 40th class by which we would wrap up this project management. So, I will just give you a brief finishing touch of this course in the 40th session, but I will continue discussing the GERT concepts, which I know in the last two classes are a little bit theoretical, but if you bear with me and read the general book which is Pritzker, you will understand that what is the importance and how the AND, exclusive OR, inclusive OR concepts come into the picture, and how the series, parallel, all these things can be consumed in general concept, where both, let me remind you again, the time is probabilistic as well as whether that path would be taken is probabilistic, and this is totally different from the concept of PERT, where time is probabilistic with a certain distribution, but the path will be taken or not is not probabilistic, it is fixed. And another important point which I keep repeating time and again is basically the looping concept, which is there in GERT, but is not there in PERT and CPM. And obviously, the crashing concept which we did in PERT and definitely we did not do in CPM, because that would be just an extension of PERT. It can also be applied in GERT and the other methods. So, continuing our GERT or GERT, basic network analysis, the exclusive OR relationship can replace the AND relationship at node 3. So, if you refer to the slides for the 38th session, you will understand what I mean for node 3, since only one branch is received at node 3. So, if you remember very correctly, the 3 combinations of input, 2 combinations output, that was led to the GERT and the general detailed discussion about that. For the inclusion or relationship, the analysis procedure as is in the AND case, the branches of the network are now given in the next slide for the convenience of the students. So, now if you see the diagram which is there on the left, so I will try to highlight it using yellow color. So, this is the one which is there on the left, and if I am able to do the color specification, let me try my level best. It is still yellow. So, yes, so this one, so at last is green, I have been able to convert that. So, if you consider the right one, which is so called circled with the green outline, and the left one which is in the yellow outline, they are equivalent. So, let me try to basically highlight that fact. So, this is basically where my this pointer is highlighting is basically the equivalence part. Now, if you see, it is a network of only 2 branches, it can be more than 2 branches also, and this can be, if you come back to the concept of decision trees, we had, like say for example, for coming up with the this example I keep repeating, because this will bring a lot of significance of how the decision trees which we did in the initial stages of the project management also bear a resemblance with the GERT one, but the logical AND OR and all this concept may not be there in the decision trees, but it definitely makes sense to repeat that. So, if you consider this path which is leading from S to 1, S to 2, and correspondingly again going out from 1 and then 1 to 3, 2 to 3, 2 and onwards. So, this circular one which I am now highlighting with the red color, this diagram or the node which is there, which you remember there were 6 of those input output concepts. So, basically they are signifying that. Now, if you extend it onto the right hand side, just understand the node which is now connecting 1 and going forward and 2 is going forward have the corresponding probabilities as given in the previous diagram, which is the one which is outlined in yellow. So, the probabilities are 1 minus P b and the time is t suffix d. So, both are probabilistic in the values depending on what the probability distribution is and what are the chances. And similarly, the node which is leading out from 1 is the probability is 1 minus p suffix a comma t c, which is basically the time taken. And the equivalent output for this yellow one and the green one, if you pay attention, I will not go into the details, because going to too much of details for the GERT would basically make it much more very technical and mathematical oriented. But just try to follow the concept using the AND OR concept, you will find out there is equivalence between this structure, which would make sense that trying to replace a probabilistic network with a less intense probabilistic network is in some way trying to replace the decision trees with their equivalent values of the expected values, that is the net present values which we have discussed. The reduction process which we try to discuss and we will try to bring into any of the GERT network involves the enumeration of all the mutually exclusive so called tasks or alternate methods of realizing 3 from node S. So, where is 3? So, let me come back to 3 again, and I highlight it in this left diagram, the right diagram, this is 3, and you are trying to basically realize that node 3 from S, which is basically considered the source using any different routes you can take. So, these mutually exclusive alternative methods enumeration, when we do it, are like this. So, first I will read and explain the description which is on the first column, then I will go to the probability and then the equivalent time. So, the branch A, but not branch B is taken. Second one is branch B, but not branch A is taken, and the third one is branch A and branch B is taken. Now, when I am speaking these words, have a detailed look at the second column, that will make sense. Now, if branch A, but not branch B is taken, so if you consider the actual route, the probability was already P suffix A. Now, if they are mutually exclusive and we are trying to find out the concept of probability, it will basically be from the point of view of the Venn diagram would be the intersection of A and B. So, I will just draw the Venn diagram in a very simple sense, which would not at all be required to basically to understand project management as a concept, but it will give you a clear picture that how the AND OR and this exclusive OR, inclusive OR and the AND concept are being brought into the picture, considering the mutual exclusive concepts of the alternative methods. So, if you have a set A and set B, so this would mean basically it is A. So, this is A, this is B, this is A intersection B, and obviously, if I go to the highlighting one using the green one. So, if I highlight this the green one, which is the whole area, so this will become A union B. Now, if you consider this one which I have just noted down, this means A intersection means that branch A and but not branch B is taken. So, obviously, it would be the initial condition or the probability which is P suffix A. If you come to the next one, branch B, but not branch A is taken, which would mean again it would be intersection P intersection B, but it now would be subtracted from the concept that branch B is taken and not branch the intersection of A and B. So, in the initial case it was P A minus P A intersection B, and in this case it was P B minus P A intersection B. Now, if I want to extend that, like there are branches A, B, C. So, obviously, it would mean the intersection concept and the minus concept would just be extended in a similar manner. Say for example, it means that the branches are due to the concept of mutual exclusive alternative method properties, we may have P A plus P B minus the concept of P A intersection B intersection C. Now, I would like to basically finish this slide and go back to one of the decision trees concepts related to the problem of the oil rig and drilling example. Similarly, in the last row you have branch A and branch B. So, obviously, it has to be both of them are taken, hence it is probability of A intersection B. And the corresponding time values if you take, if it was branch A and not branch B, obviously, it would be T suffix A, it basically becomes a very simple logic. Similarly, when I come to branch B not branch A, it becomes again a simple logic that the time would be corresponding to T suffix B. And the last one which you see, which is the last row, which is branch A and branch B, technically it means is an intersection, hence it would be as per the concept of the logics of exclusive OR, inclusive OR and AND concept, it would basically be simple minimum of the two values of T A comma T B. Now, if you remember just few seconds back I said that I will bring some simile or some similarity with the problem which we did under the oil drilling problem in the decision trees. There you had the conditional probabilities. So, conditional probability that the whole well or the geological structure was wet or dry, depending on that you had a huge amount of probability of finding out the oil. Now, in the similar way, if you consider this concepts minimum or the intersection one, it means that the condition that concept A or task A or the activity A would be taken up would depend on the fact that whether B is realized or not realized. So, hence the concept of conditional probability would come, which would mean that, let me write it down, that P A given B has already occurred. Now, this I am writing for the first time, but people with simple basic concepts of probability will understand that. So, it would mean that P A intersection B divided by P B. That means, provided B has occurred, what is the probability that A would also occur. So, you can extend it, say for example, probability of A given B and C has occurred, and you can proceed accordingly to whatever level you want to make. So, which means that the number of so called branches, number of sub edges and the nodes would be much more in number in the GERT process. So, continuing discussion in this selection, the equivalent network will be derived from following three basic networks, which is the series one, which is the parallel one and the self loop one where you have a loop. So, if you remember the series one, it would have some implication with the max and the minimum time and the max circuit and the minimum circuit. So, series I will very simply consider from the point of view of simple series circuit which can be drawn in electrical engineering. Similarly, you will have the parallel circuit similarly on the same line from electrical engineering, and the looping one which you are considering that fact that looping is allowed in GERT process. The derivation will be accomplished by enumerating all the possible paths or all the different type of occurrences which can occur from the starting node, which is the source. If you remember the source S which I have been mentioning time and again, like in the last to last diagram, S was leading to 1, S was leading to 2, S was leading to 3. So, S is basically the source, S in the end can be a sink also. So, that is the nomenclature we have to change how sink is denoted. So, starting from the starting node source to the network to the terminal node, as I mentioned, is the sink. A generalization of the derivation procedure based on flow graph theory, the graph theory which we have, will then be made, and we will try to understand how they can be utilized in the GERT process. The generalization permits the analysis of networks where branches represent activities having duration described by the random variables, which is T suffix A, T suffix B, what I have been mentioning. To simplify the terminology, a node will be described by its input relationship. So, what are the different type of inputs from where they are coming? Where no ambiguity is thought to be present, we will basically try to generalize them through using the input, or else we will specify them how they can be described. So, the figure we are going to consider illustrates the equivalent one branch network for a series, a parallel and a self loop network, all of whose branches have constant time parameters. So, we are considering time as a constant thing and whose nodes are the exclusive OR. So, it can be done for inclusive OR also, it can be done for the AND network also, but we will concentrate on the XOR, which is the exclusive OR. So, now the diagram or the slide which you have in front of you basically describes the concept which I just mentioned 2 seconds back, the time parameter, and it is basically for the exclusive OR network. And there were 3 concepts which you are trying to bring, one is the series one is the parallel one is the looping one. So, the first column basically states those characteristics. The second column basically with the diagram one represents with the constant time. So, if it is flexible time, it can be done accordingly. That flexible means the probabilistic time. The equivalent probability is given in the third column and equivalent expected time is given in the fourth column. So, now we will proceed correspondingly. So, to make life simple, so let us first consider the diagram and simultaneously try to explain the probabilities and the time, which is basically we will follow the concept each row. Now, if it is a series circuit, let us go consider this problem in the other way. So, if it is series one, let me draw a very simple series circuit in electrical engineering, and let me mention is R1 and R2. R1 R2 very simply consider them, they are to be the resistance. So, if I want to find out the resistance, technically it would be done as per the concept of electrical engineering, where you find the addition values and proceed. And if it is probability 1, they would just be multiplied, in the sense that provided R1 has happened, what is the and R2 has happened, what is the probability that the information flow or the path would be taken up would just be the multiplication of the probabilities of R1 and R2, which is in this given as P suffix A and P suffix B. And the corresponding time would be, because you have to traverse both the paths, and if they are series, so obviously it would be sum of the times being taken to traverse path A and B. Now, if I go to the concept of the parallel circuit, the concept of trying to find out the parallel relationship is just the reverse, where in this case we will just, because they are running parallel to each other. So, R1 R2 are like this. So, this is R2 and this is R1. So, this was series in the concept, this is the parallel concept. So, in this case, rather than multiplying the probability, we will just add the probabilities, because that the probabilities is considered in such a way that the sum of the probabilities will give you the probability of trying to traverse the parallel path, because the information has to flow through both the parallel paths. And if you use simple electrical engineering concept, very simply, which anybody does in class in the first years of engineering, the formulation of the equivalent time would be given as it is given here in the second row, which is probability P A into T A plus probability P B into T B divided by probabilities of A plus B. Now, if I have 3 circuits and all of them are parallel, the concept would just be extended, where it will be P A into T A plus P B into T B plus P C into T C, where P C and T C's are the corresponding probability and time for the C's path or the arc or the circuit, and that would be divided, that would come into the numerator, and the division would be done by the denominator, where the denominator would be P A plus P B plus P C, and it can be extended accordingly. So, if you go to the series circuits, it would be again accordingly. So, if there are 3, it will be P A into P B into P C, time would be T A plus T B plus T C. And in the self loop one, we basically have to see that the loop is coming inside depending on what is the start and what is the finish. So, if I have the probabilities, the probability would be I have traversed PA and then it would be coming back. So, it would be divided by 1 minus PB and the corresponding time would be calculated as given, which is TA plus PB divided by 1 minus PB, which is the actual equivalent probability multiplied by TB. So, this is TA, this is TB, and the weighting one or the weighteds or weights which is happening due to the looping one would be PB into 1 minus PB. And if there are 3 corresponding such loops which can be made complicated as possible, we can find out the equivalent structure and their equivalent probability and the equivalent time. Since for a series network both branches must be taken to reach node 3, the probability of taking both branches is the product as I mentioned of the individual probabilities, and the time is the sum of the individual times as I just mentioned, and which is there in the first row in the last slide. For the parallel branches, either branch can be part of the realization, but not both by definition of the exclusive OR concept, and based on that we calculate or give the concept. Thus, the probability of going from node 1 to node 2 is the sum of the probabilities. So, if I am basically going from 1 to 2 depending on whether the parallel and the series, it will be calculated accordingly. The time to traverse from 1 to 2 nodes is no longer a constant but taken on the value TA with probability PA and TB with probability TB. So, PA is the probability and the TA is the time, and corresponding for B, PB and TBs are the corresponding probability and the time. Now, if I want to normalize things, so that means I want to basically bring a similarity in the comparison, normalizing P and PB by dividing by the sum of the probabilities. So, it will ensure complete density function for the equivalent time as accounted, and then we will have the equivalent expected time and the expected probability as calculated. And again I am mentioning it can be extended for more than 2 of these connections, which is possible in any complicated GERT process. It should be clear that a complete description of the time to realize node 2 has not been obtained, and the use of expected value to describe the time parameter is an approximation based on which we are trying to proceed. Now, why it is an approximation? If I remember that these realizations are random. In the similar way, in one of the classes, last 2 classes, I discussed that if you have a box and chits are marked 1 to 5 and then you pick up chits only 3 in number. So, the average will itself be random, but in the long run as you keep doing that experiment, then the averages of the averages would be actually equal to the expected value of the population. Population means the whole set, that means chits 1, 2, 3, 4, 5, there cannot be any other set of observation apart from that set of chits. So, even the population should be infinite, but I am trying to basically give you an example of how these things can be understood. So, reduction of the self loop, the loop which was the third diagram which was there, to an equivalent probability and an equivalent expected time is obtained by summation of the probabilities, and the probable times to all possible paths node 1 to 2. So, if it is 1 to 3, it will be done accordingly. The probability of going from 1 to 2 with no transition around self loop is PA. With one transition of self loop, the time would be, as they are in series, it will be PA into PB. With transitions being n in number, obviously it will increase. So, first time it is PA into PB, second time again it happens, it will be again PA into PB. So, if it is happening 2 times, it will be PA into PB square. So, both of them square. 3 times it is happening, it will be PA into PB, both of them cubed, and if I do it n number of times depending on how many loops or looping is there, it will be calculated PA into PB to the power n. Summing would yield basically the equivalent values, probability being PA 1 minus PB. Similarly, the expected value can be found out using the simple summation. So, what we are doing is that trying to find out the equivalent summation for number of such iterations being from n is equal to 0 to n is equal to infinity, and you can find out the probabilities, and these values which were given in the last diagram or last table. So, what we did, it was trying to basically sum it up from 0 to infinity and then find out the equivalent probability and the equivalent time. So, now where it says the normalization factor is P A divided by 1 minus P B, note that the parameter of the C branch must also be altered by the same factor if the self loop is removed from the network. Again, the expected time does not completely describe the network, because expected values and the times would be taken into consideration to study the network for the GERT process. From the analysis of the basic networks represented above, it is seen that for two branches in series, the probabilities associated with the branches are multiplied to obtain the equivalent probability for the two branches. For parallel branches, the probabilities add up. So, this rule adheres to the basic law of nodes presented previously for flow graphs. So, whatever the concepts of the flow graphs are, the concepts are just being extended in this case, which means that the probability associated with a node can be computed at the sum of the probabilities of each incoming branch times the probability of the node from which the branch has emanated. So, if you see it, the multiplication and the normalization has been done in such a way that it basically adheres to the flow graph concepts. Alternatively, by setting all times on a stochastic network to 0 and allowing the other parameters to assume a wider values range of values, reduces a stochastic network to a flow graph, and that can be done. But we will study these points from the point of view of the stochastic network, considering in the initial sense, in the general way, that both time and the path which is being followed are both probabilistic, and they are given by P suffix the path, T suffix the path number or name, whatever it is, A, B, C, 1, 2, 3, 4, as it is mandated by the concept which you are trying to utilize. It is now possible to state the relationship between the PERT type network and the flow graph and the stochastic network. So, let me go through the important relationship slowly, and I am sure you will understand that. Point 1 is PERT type networks are stochastic, that means they are GERT variety networks with all and deterministic nodes. So, it is basically and the deterministic combination. So, if you go back to the combinations which we have 3 into 2, that is 3 inputs and 2 outputs, if you combine them, one of them were basically the and deterministic one. Flow graphs are stochastic network with single multiplicative parameter. All additive parameters such as times are set to 0 depending on how you assume. The probabilistic interpretation of the multiplicative parameter is removed in order to basically make sense how they can be done. So, let us return to the discussion of the flow processes, returning, and with that we will go into details in the 40th lecture. So, let me read the slide which I will try to explain to the students. Returning to the discussion of the reduction of the basic networks, it is seen that the time parameter is added for two branches in series and is a weighted average for two branches in parallel. These observations suggest the transformation of P and T into the single function based on which you will try to basically find out what is the probability and what is the time for the overall network. If you remember in one of the slides, initially when we started the GERT process, we said that we are interested to find out the moment generating function, because that would give you the actual characteristics of the probability and the time. So, we will take the single function which will mention as W function here. So, then for two branches, the W functions would just be the multiplication. So, for W E, which is the expector of the average value, for S or the source of the sink, whichever you are trying to realize, or S can be just be utilized as it is, it will be, if there are two, it will be W 1 into W 2, and W 1 would be given by P 1 e to the power S T 1, and W 2 would be given by P 2 e to the power S E 2, and for two branches in parallel they would just be the sum. So, series would be multiplication and the parallel would be summed. Differentiating with respect to S, we will try to basically find out what is the characteristic functions of the properties, and based on that we will proceed. So, with this I will close the 39th lecture. and with a note that I will try to wrap up GERT in the 40th lecture, and also try to basically go very briefly about what we have covered. We do agree that considering the 40 lectures, we had to cover a lot of things, and we tried our level best in going through that, but I am sure the students would have really learned a lot of new concepts once we end the course, and I will try to basically highlight that in the last class. Thank you very much for your attention. Have a nice day.